Welcome back to my channel. Let's explore today another interesting concept about the universe in which we are living. Thank you again. If you could subscribe, will help me a lot to calibrate my messages to a broader audience. Leave me any comment in the comments section. I will see them for sure and I will answer if deemed necessary. So without further ado, let's start. According to our understanding of the universe, the cosmic background radiation of the universe had enough energy just 15 million years after the Big Bang to keep the entire universe at a comfortable 300 Kelvin for 3 million years, which was sufficient to support liquid water everywhere. There was a possibility that life may exist everywhere in the cosmos during this cosmologically tiny period of time, without necessarily needing to orbit a star for energy. The only additional necessary components were heavier elements like carbon, which were created by early stars. Can life really start that early? Most likely not. Only hydrogen and helium were generated in the first 20 minutes following the Big Bang under the hot, dense conditions, combined with a minor abundance of heavier elements and a trace amount of lithium, 1 in 10 billion atoms. The existence of water and organic chemicals, however, which are necessary for life as we know it, had to wait until the first star's innards, around 50 million years later, fused hydrogen and helium into oxygen and carbon. The generation of the necessary elements was the first life's bottleneck rather than a proper temperature, as it is now. How long ago did life actually begin, given the initial scarcity of heavy elements? Billion of years before the Sun, the majority of stars in the cosmos were born. In the last few billion years of cosmic history, life most likely evolved near Sun-like stars. But in the future, it might still manifest on planets revolving around dwarf stars like Proxima Centauri, our nearest neighbor, whose life expectancy is hundreds of times greater than the Sun's. In the end, it would be preferable for humanity to move to a planet that is habitable around a dwarf star like Proxima Centauri b, where it could keep itself warm close to a natural nuclear furnace for up to 10 trillion years into the future. Stars are merely fusion reactors constrained by gravity, with the advantage of being more stable and durable than the magnetically constrained versions that we produce in our laboratories. Water is the only liquid, as far as we are aware, that can support the chemistry of life. However, there is still a lot we don't know. Could the warming caused by the cosmic radiation background alone have led to the emergence of alternate liquids in the early universe? Ethane and propane may have been liquids sometime after the first stars formed, and ammonia, methanol, and hydrogen sulfide may have done the same. These compounds can be investigated experimentally, but it is uncertain how important they are to life. We could investigate whether life can develop in liquids other than water if we ever succeed in generating synthetic life, as has already been attempted at Harvard University. Examining if life originated on planets near the oldest stars can help us understand how early life in the universe began. These stars are anticipated to be poor in metals, or elements heavier than helium. In fact, metal-poor stars have been found in the Milky Way's outermost regions, and they have been identified as potential members of the universe's first star-forming generation. These stars are carbon-enhanced metal-poor because they frequently show an augmented abundance of carbon. As a result, we may look for planets that transit, or pass in front of these carbon-enhanced metal-poor stars, and have atmosphere components that contain biosignatures. Based on the ages of these stars, this would enable us to calculate how far back in time life may have begun in the universe. On the basis of long-lived radioactive elements or the size of scars left by dust particle hits on the Moon's surface, we could determine the age of interplanetary technological equipment that we might discover drifting close to Earth. Finding technical remnants from ancient, far-off civilizations that were able to harness enough energy to make their signals audible across the huge cosmic scale would be a complementing approach. A light flash produced by a collimated light beam used to power light sails could be one potential indication. Others might be connected to cosmic engineering initiatives, such shifting stars. since the signal travel time would take billions of years in each direction and no participant would be patient enough to engage in such a lengthy exchange of information, communication signals are not likely to be detectable throughout the universe. But the imprints of life are transient. The outlook for life in the far future is bleak. In 10 trillion years, all life will likely be extinguished due to the dark and icy conditions brought on by dark energy's fast expansion of the universe. We might treasure the passing gifts that nature had given us up until that point. If our activities support a civilization that is sophisticated enough to last for trillions of years, then our successors will be proud of what we did. We can only hope that we will make sensible decisions so that their big history books will remember us kindly. The universe is a big place and is full of mysteries. This is it for today. Please join me next episode when we will unfold another cool concept of modern physics. Thanks for watching.